Well, I'm just going to give a brief update, kind of combining something that's already been discussed on quality assurance. And I will talk about data-driven precision. So precision in terms of where we can get the proper data in and make the best use of existing tools, including AI. I'm Ilya Gipp. I'm the Chief Medical Officer at GE Healthcare. So I'm going to be talking about some of the things that we've done recently. And it's not going to be exactly a technology update, but more on the ideas that David just referred to. Number one is there's definitely room for improvement. If I look at lung biopsies in terms of the necessity for precision in decision making, we can see that maybe some of the publications that a little bit earlier that showed that about 30% of interventions were done on benign lesions. And even if we go to a more recent papers, that number doesn't really change. There is even a whole language that's been developed to talk about invasive procedures that yield a benign diagnosis. So therefore, obviously, there is room for improvement. Now, one of the things that is being used is the better characterization of the lung nodules. And to start with, one of the models that is there is the Brock model. And I'm not going to go into the details, but the important factor here is that there is a nodule size. Now, the question is, of course, there is more to be done in terms of radiomic features to be also implemented. But if we cannot identify the size properly, then how can we trust the other features that are in the images if the images are eventually not accurate enough? So there is a quantitative CT and pulmonary nodule characterization that starts with detection by itself. So here it is, the initial detection, and then the volume is being evaluated, and then the timeline kicks in. And based on one of the characteristics is how fast the nodule growth, because, well, with the malignancy, the faster growth. So we can see whether that is, well, hopefully benign, maybe a little bit higher risk of malignancy, or malignant and there's some theoretical limit, but in general, this is what we try to do is we try to evaluate the growth curve and identify based on the initial measurements what's the follow-up is going to be. And well, in this case, unfortunately, but the necessity for accuracy is coming from the fact that there is a certain error that is naturally in any kind of data. And the bigger this error is, the higher the chance that if I basically put a line, that at initial detection, we can be on one side of that deviation. And then in the second measurement, we can be on the other side and we can potentially misjudge. And that's where the necessity for accuracy is coming. Now, this is an interesting paper that I just ran across that actually is not exactly coming from exactly the healthcare world, but it more talks about the data, which I think is very well relevant for this discussion, is the image quality assurance that has been well recognized. A recent paper, and then if I just quote one thing here, the quality and sharpness of the recorded images have the greatest influence on image analysis. And the other part also over here, so when confronted with broader circumstances, medical image analysis systems frequently fail to satisfy the needed quality criteria and are abandoned. I think that this is ultimately what needs to be the idea for the greater accuracy. So something that we've done, and I've reported some of this in the previous meetings, we used a phantom that was provided by Acumetra, and we focused on 6 millimeter ellipsoids that represented the nodules. And the reason for 6 millimeters is, this is what I usually say is where the business is, because 6 millimeter is the lung RADS cutoff size with either 6 or 12 months follow-up. And please note that 6 millimeter diameter sphere doubles in volume when it only reaches 7.6. So the accuracy of the CT data in identifying the size needs to be quite high. What we did is we took one of our scanners, in this case, Revolution Apex, and we used a standard protocol that was identified by the KIBA as well as ACR guidelines. Then we took the default protocol that the scanners are coming with. And remember, as a GE Healthcare, we're not defining the protocols, but we can definitely optimize this. And this is exactly what we've done by taking this into the third column. Now, the thing is that all of the protocols, they satisfy the requirements for the low dose CT, but there was definitely room for improvement, what we have identified. Now, the scope of the experiment was to identify the precision, the bias, and the ability to get them better. I'm not going to go too much into the details, especially having the clock ticking in front of me, but the smaller the precision is and the smaller the bias is the better it is. And I know it's a little bit counterintuitive because, well, the precision is supposed to be higher, but the precision is the deviation between the measurements. So the smaller it is the better. And this is what we've done. So we took 3 protocols, we identified those spheres, and this is what we have obtained and then used the software, the open source software that was provided by Acumetra as well. We've done the measurements, and this is what we came up to. So the volume bias, and remember, I already mentioned this, the less is better. So this is the standard. This is the default protocol that is on our scanners, no matter where they go. And then this is the optimized, and we're able to actually go below by about 49%. And the volume precision, again, less is better. This is the standard, this is the default, and this is the optimized. So just by doing this, we went down in 53%. What it actually means is switching from Kiba, small lung nodule, so recommended base standard, to optimized, resulted in a volume bias improvement of 49 and 53%. So as a key takeaways, greater accuracy in small pulmonary nodule assessment elevates the value of CT data in early detection of lung cancer through enhancing decision-making. CT scanners, in despite of what scanners we're talking about, have the potential for more accurate assessment of small off-isocentric nodule sizes, because also the position of the nodules is mattering. And it pays off. For a sphere model, 12 to 15% error in diameter measurement is 40 to 52 error percentage in sphere volume assessment. So it's actually kind of like becomes cubic, actually not cubic, it's power 3. And then ALARA principle for lung nodule assessment might better be complemented by as accurate as achievable. So as low as achievable, so as accurate as achievable. So DOSE to an accuracy principle, enabling greater data-driven precision. And I would like to recognize the team that helped to put together the study. So we're also working on the paper that hopefully will be out later this year. Thank you very much.